First of all, I apologize for postponing my talk many times due to some personal reasons. So, anyway, today I'm going to talk about a new kind of construction arising from finite simple connected graph, which turns out to have some interesting properties and connections. And this is a joint work with Apurva Kare. Let us first set some annotation. Recall that a graph G is a pair B and B, where B is a set of vertices and E is a set of paired vertices whose elements are called edges. And in this talk, all my graphs are finite, simple, unweighted, and most importantly, connected. Because the graph is connected for any two nodes B and W, there is a path connecting these two nodes, which cannot be eliminated. So look at the all possible such paths and take the path of the shortest length. And I will denote this length with dBW, which is clearly a non-negative integer, and it is equal to 0 if and only if p equal to w. With this number dBW, we form a vertex and vertex matrix called the distance matrix of the graph, whose dW element is dBW. The determinant of the distance matrix of a tree studied a lot in the literature. Recall that a tree is a connected graph with no induced cycles, or in other way of saying, it is a connected graph with n nodes and n minus 1 edges. Here are some examples of trees. Our work is motivated by two sort of classical facts. The first fact is is algebraic. That is an interesting phenomenon on the distance matrix of three fs. This is a result by Graham and Pollack. To illustrate this, there is an example. Take these two tree on 4 nodes. Clearly, these are not isomorphic. Now look at the distance matrices. For let's say for the first graph, the vertex 1 is adjacent to 2, 3, 4. So obviously all the diagonal entries are 0, and 1i entries are 1 for I equal to 2, 3, 4. Similarly, the vertices 2 and 3, 3 and 4, and 4 and 2 are at a distance 2 from each other. This gives us distance matrix for the first graph. Similarly, for the first graph, it turns out that both the matrices have same determinant, and this is a result by Graham and Pollack, and they proved in 1971 that the determinant of the distance matrix is on n nodes is a function of n, and it's independent of tree structure. And this is a very remarkable result. So this provided us our first goal. We want to find other families of graph for which determinant behave nicely. I will explain the term nice in the next slide. Okay, so the second fact which motivated our work comes from spectral theory. Ron Graham again studied the spectral side of distance matrix of tree with Lovash in 1978. Since then, this has been studied several times in the literature. One question is natural to ask. It is clear that the distance matrix itself dictates the graph. So just look at the entries which are 1. Those correspond to the edges, and if you know the edges, you know the graph. Now the question is, do the eigenvalues of the distance matrix determine the graph structure? or in other way of saying, does the characteristic polynomial detects the graph itself? The answer turn out to be no. There are graphs. For example, these two graphs here on the same number of nodes. So the distance metrics are of the same size and characteristic polynomial of the same are of same degree. The characteristic polynomials for these two graphs agree, but these two graphs are not isomorphic. For example, the vertex 2 here the vertex 2 is of degree 4, but there is no vertex of degree 4 in the first graph. So in particular, we can conclude that characteristic polynomial does not detect the graph. This gives us two interrelated motivations or goal. We want to find other family of graphs GI indexing by some set I. For example, family of trees on fixed number of nodes, such that the function I goes to determinant of the distance matrix is a nice function. For example, here the function is a constant function and is a purely number in terms of the number of nodes. And so we want to find other such family, and more importantly, the first goal should relate to the second goal. This family help us to find an invariant which detects the graph truly. The distance matrix, of course, it detects the graph, but that is not much interesting and deep. We want some kind of polynomial invariant, and at the same time, that invariant should relate to the distance spectrum of the original graph. So the goal of this talk is to tell you, indeed, these goals or motivations are achieved with the same object. The object that I want to tell you about is Blowup-polynomials of graph, and the family is graph blow. And let me begin with the family, then I'll come to the invariant. The key construction which will answer both of these questions and reveal many more interesting facts beside the graph blow is following. So the key idea is to take a couple of positive integers indexing by vertices, and we call the new graph as G determinant. This is again a finite simple connected graph, and the nodes are given as following. For NB, the integer for NB, the integer I have chosen, take that many copies of the vertex B, and all the copies of a vertex are joined to all the copies of another vertex if the original vertices are adjacent in the original graph. And if the original vertices are not adjacent in the original graph, then the copies are not adjacent. Here also note that a copy of a vertex B is not adjacent to copy of another copy of the vertex B, because I am letting self loops in the original graph. So the definition, I think this construction is clear. So let me give you some examples. The first one is that of a path graph on 3 nodes. So forget the node 3 first and just look at the edge AB. Now take one copy of vertex B and take 2 copies of vertex A. And now A is adjacent to B, and the new copy that I will see is also adjacent to B, but A and C are not adjacent. Thus, the path graph on 3 nodes is a blow-up of 2 nodes. Here are two more examples. One is a star graph. One is a star graph. This is same as saying that start with an edge and take n copies of the one vertex and fix the other vertex, and that will give you exactly the star graph. Similarly, for a cycle graph on 4 vertices, start with an edge, let's say 1, and now take two copies of the vertex 1, say 1 and 3, and two copies of the vertex 2, say 2 and 4. Now 1 is adjacent to 2, so 3 must be joined to 2, and 3 must be joined to 2. So 1 and 3 are joined to 2. Also, 4 is a copy of 2, so 1 and 3 must join to 4 also. But 1 and 3 are not joined, and 2 and 4 are not joined. So these are some examples of blocks of 2 nodes. So as I said, I am interested to look at the determinant. So look at the determinant of the blocks of this graph. So if you look at the determinant, if you look at the determinant of the this family of graphs, for example, for this family of graphs, one can explicitly calculate the determinant. I won't tell you how, because in fact one can calculate this with a greater generality. Anyway, so if you calculate the determinant, then this turn out to be this expression, which is this expression is very simple and clear, and it consists of two parts. One part is exponential in r plus s, where r is the number of copies of the first vertex, and s is the number of copies of the second vertex. Then a polynomial in the sizes r and s. Note that interestingly, the distance matrix consists of only 0, 1, and 2, and the sizes of the determinant, sizes of the matrix include r and s, but this expression is a function of r and s. This is very interesting. So now the question is, what is the determinant of graph blocks for more general graphs? Does it have something similar? The answer turned out to be yes, and this is our first result. There exists a real polynomial Pg in the sizes. So the argument of the polynomial are in the sizes of the matrix, and the following things happen. The determinant of the distance matrix of graph blocks is equal to minus 2 raised to some summation of sizes minus 1 times some remaining factor, and this remaining factor is a polynomial in the sizes, and this expression is true for all possible is true for all possible sizes of all possible tuples of positive integers, and moreover, this real polynomial which is multi-affine in n with the constant term minus 2 raised to number of vertices in the original term and a linear term given by this expression. In fact, we have closed from expression for every single monomial. The real polynomial PGM what we define to be blow-up polynomial of graph covers all possible blocks of the graph G, and this attains our uh, first goal. Here the family is parameterized by this bold N, and the G bracket N, the G bracket N, the family for which the determinant is the determinant is some nice exponential function times the multi-affine polynomial, and this covers our first goal. So the second goal is to connecting this polynomial to distance spectrum characteristic polynomial and recover the graph. Before I go there, I'd like to mention one thing about the proof. We prove this result in full algebraic and greater mathematical generality over a commutative ring. The proof uses something called Jarovsky density from commutative algebra. So the idea is, first of all, define the modified distance matrix, which is exactly this matrix, and the diagonal matrix delta with sizes on the diagonal. Then the proof reveals that minus 2 raised to some power of this determinant is equal to PGN, and this is further equal to determinant of this matrix. And determinant is of course a polynomial. So this block polynomial PG is also a polynomial. You see in both sides of this equality there is no notion of mg being invertible. So I don't need mg to be invertible, and it is not taken in either side of this equality to claim. But to prove this inequality, the proof uses the inverse that gets used does get used. So now the question is, how one can assume in general that these inverses exist in a commutative field? The answer is exactly the title of this slide, using Jarovsky density. Before I go these steps, let me explain this with an example. So if we work over a field of real numbers, let me tell you how. So if we know this equality holds for that mg not equal to 0, then using the continuity of the determinant function and density of the invertible matrices, one can prove this result for a field of real numbers. Similarly, if we work over a commutative ring, unital commutative ring, the usual topology will be replaced with Jarovsky topology, and usual density will be replaced with Jarovsky density. And here, instead of continuous functions, we have polynomial functions. And if two polynomials agree on a Jarovsky dense set, then they agree everywhere. And the Jarovsky dense sets are exactly the non-zero locus of the non-zero polynomial. So if these polynomials agree on the non-zero locus of this polynomial, then they agree everywhere. So this is exactly what is written here. This step. Okay, maybe I'll skip this step. Jarovsky density is a powerful technique. As you see there, you can ignore the notion of invertibility and work over a commutative ring. This formula for we put in the paper this formula for PGN, and we also proved this. The PGN is a function of sizes. So from now onwards, in my talk, we will use NB to denote both sizes as well as variables. So what I said, PGN is a multi-octal polynomial in the sizes. So for example, this is the polynomial for algebra, uh, and the coefficient of every monomial, the coefficient of every monomial, as I told you, can be computed explicitly. So and it equals to minus 2 raised to some power times determinant of the principal submatrix of the modified distance matrix corresponding to this subset I. So one can compute this all the monomials explicitly. Okay. Uh, so first of all, this achieves our first goal. The function the function indexing the variable uh, to the determinant of the distance matrix is a nice function for all graphs P. So now the question is, what about the second one? Can this polynomial recover the graph G itself? Before I go there, let me tell you about related polynomial to the Blowup-polynomial, and it's called univariate polynomial, where I said every NB to be equal to n, and and every NB to be equal to n, and this univariate polynomial is closely related to the characteristic polynomial of distance matrix, right? So this is our next result. A real number n is a root of univariate polynomial if and only if first of all n can never be zero. That is because zero is never be a root of univariate polynomial, and then n not equal to zero. So we can define this quantity, and this is an eigenvalue of the distance matrix with the same multiplicity. So the univariate specialization of Blowup polynomial connects to the characteristic polynomial of the distance matrix. Now the question is, can this univariate polynomial detect the graph G? The answer is no. In particular, the same two graphs that I told you demonstrate that the univariate polynomial certainly does not detect the graph, and it's equal and it equals for these two graphs, but these two graphs are not isometric. This leads us to the same original question: does the multivariate polynomial detect the graph? Let me uh, um, let me tell you about a quicker question first. If G has an automorphism, by the term automorphism, I mean uh, if we if the leveling of 7 and 8 gets switched, the graph stays isomorphic. There's nothing changed in the graph. Similarly, if 3, 4 gets switched or 4, 5 gets switched there, the graph stays isomorphic. So if G has an automorphism sending a vertex B to W, then the Blowup polynomial is symmetric under this operation. Thus, the self-isometries or automorphism of B determine the symmetries of the Blowup polynomial. Now the question is, if I know how my Blowup polynomial is symmetric in the variable, can I understand the automorphism of graph G? This is the weaker question, and of course the stronger question is, can this Blowup polynomial detect the graph from which I from which I could understand the automatism of G. Our next result answer both of these questions, and here is our result. The symmetries of PG, if the symmetries of PG is the same as the isometries or automorphism of graph G, and more strongly, the purely quadratic or the Hessian part of the Blowup-polynomial depicts the graph G. So I don't need constant linear term for higher order term. Hessian alone is sufficient to recover the graph G. And then for all graph G, one can actually perform this calculation with an explicit calculation. One can show that the left hand side is exactly same as minus 2 raised to some power times all one matrix minus again minus 2 raised to some power times this formula, from which it is easy to identify the distance matrix. Thus, Hessian matrix gives you the distance matrix and vice versa. And if you know the distance matrix, again you know the graph. This answers our both of these goal, and now we have we do have a nice familiar graph for the graph block for which determinant behave nicely, and determinant themselves are symmetric. Themselves are multi-affine polynomial in the sizes, which turn out to be connect to distance spectrum and characteristic polynomial, and we also relate this to this also recovers the graph G. This ends the this will end the first part of my talk about Blowup-polynomial and graph plots. In the next few slides, I'll talk about some other properties of this polynomial. Remember the polynomial PK2. Remember this polynomial PK2, which is multi-affine polynomial. Let me specialize these two univariate polynomial. Take R equal to S equal to N. Then this univariate polynomial is 3n square minus 8n plus 4. And this is the polynomial. And this is clearly factorized. So it is a real number. And this is for graph K2. One can also take the block of complete graph, and you can block of complete graph, and for this also univariate polynomial is real number, and this one can verify it. Now the question is it real number for all graph G? Answer is yes, but in fact much more is true. Real rootnets is a one variable manifestation of a more general and powerful notion called real stable polynomials. And a polynomial is a in k variables with real coefficients and complex argument is said to be real stable if it is non-vanishing in the upper half. So, and so here is our result. The Blowup polynomial PG is real stable for all graphs. The point is real stable polynomials are real stable polynomials and their generalizations are focus of tremendous recent research, and made some spectacular advances in mathematics, primarily due to the work of Roger Bendham. uh, they prove they prove far-reaching generalizations of the Lebesgue Fourier-Schur program, developed a multivariate jazz principle and Jensen inequality, a framework incorporating Lee and Hellman-Lib program, and proved three long-standing conjectures of Charlie Johnson. This progress then taken forward by Marcos Hellman Srivastava in probing the Cartesian singular conjecture and existence of bipartite Ramanujan graphs. So, this highlights this particular highlights of modern mathematics comes from real stable polynomials and study. So the point is the polynomial, the Blowup-polynomial that I mentioned is is providing new class of real stable polynomials, and it arises interestingly from graphs and distance matrices. Uh, I will I would like to mention a couple of ingredient uses in the proof of this theorem. First one is a result of Brendan from 2007, so which says that if you have positive semi-definite positive semi-definite real symmetric matrices and a real symmetric matrix B, then this function is real stable. In other words, take the linear combination of the positive semi-definite matrices with variables as a with this variable as coefficient and add the matrix B to it and take the determinant, then this function is real stable. And another result is inversion preserved real stability, which says that if you take any variable, let's say z1 with degree d1, and if z1 raised to d1 times this polynomial is real stable, if this original polynomial is real stable. These two facts and with some clever determinant calculation turn out to prove this theorem. Now let me go beyond real stability. I remind you from the very first result that I mentioned. The Blowup-polynomial PhD has this as a constant term and this as the linear term. So this already shows you immediately that this polynomial does not satisfy two sort of desirable properties. The first one, since the first one is that the coefficient of linear and constant term of our unequal sign, and this is the first property. To bypass this, one can take p2 of minus 1. So this will give the minus inside this quantity. So the linear and constant terms are equal sign. Now one must also check the higher order cubic and quadratic term. Are those also have the same sign? Maybe they are or may not. And similarly, there is a constant and linear term in this polynomial PhD. So the polynomial is not homogeneous. For this, there is a standard trick of homogenization, and if you want to bypass these two steps together, then you can take minus inside this function. Now the question is, why do I want to bypass these two obstacles? The answer is that the real stable polynomials with these additional properties were started in even broader settings, setting by Gautier, Brenton, Leggett, and they call it strongly Rayleigh polynomials. With all the coefficients are of the same, are of the same size, and homogeneous stable polynomials were broadly studied as Lorentzian polynomials by Brendan and Co. very recently. So now question is, if we homogenize PG at -1, for which graph G does this RD polynomial in this class or this class? Our next result explicitly characterize this polynomial, and remarkably answer is if and only if all the coefficients have same size. So to answer both of these question, we have the same family, and and this and these are from the same very familiar family of graphs. And so question, which are these graphs? So answer is exactly in the title, complete multipartite graph. So given the graph G defined is homogeneous blow-up polynomial, exactly the same as I told you, then the following are equivalent. This homogeneous blow-up polynomial that I mentioned you is real stable if and only if all the coefficients are non-negative, and if and only if you take this polynomial PG without Z but with minus sign and divide it by PG of -1, -1, -1. That is the sum of all the coefficients. Then you will get a polynomial which is non-negative coefficient, and these coefficients add up to 1. So this will form a probability distribution, and the claim is this thing will happen if and only if this distribution is strongly valid. And these three things are equivalent to the graph is if and only if the graph G is complete multipartite graph that is precisely same as saying as blow up of a complete graph. So now you can think about why this same as saying as the blow up of a complete graph. Okay. This provides a novel characterization of complete multipartite graph in terms of the strongly Rayleigh nature of the homogeneous polynomial. In fact, it provides the same characterization in terms of the Lorentzian nature. And here are four other equivalent characterizations. A graph is a multipartite graph if and only if any of the four conditions hold. The matrix, the modified distance matrix Mg is positive semi-definite. Homogeneous blow-up polynomial is Lorentzian. Or it is strongly log complex, which is defined by Kulpit in some other context and is completely log complex. So, this So these provide characterizations for the graph being completely multivector, and this will provide a novel characterization of this class. The graph Blowup and Blowup-polynomial as so far we have the graph Blowup and Blowup-polynomial, which we talked about so far, defined for finite connected graph. In fact, this can be defined in greater dimensionality, and all these results can be proved for finite metric spaces. Uh, Not all, except for one result, which do not go through, is PG recovers the graph G itself, and the block polynomial of result does not recover the metric space. See, because now the distance no longer minimal distance no longer be one, it can be any positive real number. But there is a partial progress in that direction. So if the block polynomial is symmetric in all n, even only if the graph G is complete, and we can more generally, for a finite matrices X with a distance matrix dx, now we can define the block polynomial exactly the same way, and this block polynomial is symmetric in this variable even only if X is a discrete upper meaning there exists some positive C such that the distance is C if X not equal to Y and otherwise it is 0. Okay. In the last part of my talk, in the last part of my talk, I will discuss some combinable abstraction of this result. Is called delta method. We obtained a new delta method for each graph and another one for each tree. Because that method is a structure which abstracts and generalizes the notion of linear independence in the vector space. So a finite method M consists of is a pair E and a curly this curly set F. The where E is a finite set for the ground set and F is a non-empty family of subsets of E called the independent set, which satisfies the following properties. A subset of an independent set is again an independent set, and and the F is closed under independent set exchange property, meaning that if you take two independent set A and B, suppose A has 4 elements than B, then there exists an element X in A, not in B, such that B union this singleton set X is again an independent set. So this is the definition of method. This method have important application. Method theory have important application in various branches in mathematics, including topology, geometry, combinatorial optimizations, coding theory, network theory. And here are some examples of method. For a finite set mean, if we take the independent sets are the all subset of U, then obviously it is a method, and we call this method as a free method. And if independent sets are exactly those sets whose contains at most k elements for some fixed integer k, then this method is called uniform method. So here note that free method is a particular case of uniform method. So our next example is from linear algebra. Uh, take any finite subset E of a vector space and and define the independent set as the linear independent subsets of it. Then this will form a method. For example, if we take a matrix A over a field E, and here the set E is the columns of the matrix A, then then the then the independent subsets of the column space form a method. And our final example is from graph theory. Take a graph G with a set E, then can take this S set E as a ground set. We can define a method. So any subset F of E, that is the set of edges, is independent set, even only if it is a forest. That means F don't contain a circle. Okay, these are the some examples of method. But if you look at the closely at this third example, so here the independent sets are the linear independent subsets of the column space. So instead of this, if we define the independent set as the basis of the column space, then it will satisfy another interesting property, and it is called symmetric axiom. Uh, and the definition is, suppose two set A and B in F and X lies in their symmetric difference. Then there exists another Y in their symmetric difference such that a symmetric difference to this set is again lies in this kernel F. So a family of non-empty subsets F of U, a family of non-empty subsets F, which is closed with the symmetric axiom, together with this ground set E, is called the delta method, and the non-empty and the subsets are called feasible set. Delta method. Delta methods were first introduced by Projesh in 1987 as a generalization of the notion of method. And a delta method is a method if and only feasible sets all have the same cardinality. So now if you look at this example, we know that in linear algebra, basis at the basis at the same cardinality. So this method is a delta method. So each symmetric and few symmetric matrix, each symmetric and skew symmetric matrix with the ground set E form a delta method, and which is denoted by NA. Here the feasible a subset of E is a feasible set if and only if it is NP or the corresponding principal submatrix of A is invertible. So Projesh proved this for a symmetric or symmetric matrix. This set structure is indeed formed delta method, and which is said to be inner. So in my talk, I have mentioned about multi-affine polynomial, real stable polynomial, delta method. Is there any connection between these three things? Answer is yes, and this is result of Brandon from 2007. He proved that if PZ is a real stable multi-affine polynomial, then the set of monomials with non-zero coefficients form a delta method with this ground set. Remember that how Blowup-polynomial, which is real stable, as well as multi-event. So from PG from the Blowup-polynomial, we obtain a delta method for all graph G. In fact, more is true. This into more is true. In fact, this delta method is linear because the physical sets are corresponding. The physical sets are corresponding to the subset I for which modified distance matrix has a modified distance matrix is invertible. So this delta method is linear. So we denote this block delta method with as MMG. So if we take a close look at this MMG for G as a path graph, then this is this equality holds. So here, as I mentioned in the beginning, for a path graph on 3 nodes, the coefficient of the monomial is 0 because because it is a block of the block of 2 nodes, and also you can show that this submatrix, the coefficient of this monomial is also 0. And more generally, this equality holds for path graph on k nodes for small value of k. Now the question is, does this equality is hold for all k? And independent of the question 1, is the right hand side is a delta method for right hand side is a delta method for all k. By explicit calculation, one can show that the determinant of the modified distance matrix of path graph on 9 nodes is 0. So the coefficients of the monomial ni plus 1 to ni plus 8 in the block polynomial of path graph on nodes more than 9 is 0. So this gives us that the left hand side is a strict subset of right hand side, and here is our result. This right hand side is indeed a delta method, and it is equal to the right hand side if and only if k less than equal to 8. Now, question is, if this right hand side delta method can be generalized to other graphs. The answer turned out to be yes, and this for all 3. And to illustrate this, we needed basic result, and here is our result. Suppose H is a graph and n is a couple of positive integers, such that this block G bracket n is an induced subgraph of H. And B1 and B2 are vertices of G bracket n, and they are copies of the vertex B. And this set is subset of I, then the coefficient of this monomial in the original graph is 0. So, here example of this result is, if we take G as a tree, then 2 vertices are tree, and if 2 vertices are leaves in any subtree of G on the set of vertices I with the same pair, then the determinant of this modified distance, this was submatrix of this modified distance matrix is equal to 0. Now one can ask, if we set all such I as invisible subset, does it give a delta method? You can note that this recovers the right hand side of this delta method. And answer turned out to be yes, and here is our final result. For a tree, define a subset of vertices I to be infeasible. Here I am defining infeasible set. If it is planar tree, has two leaves in I, and that have the same parent. The planar tree on a set of vertex I is defined as the smallest tree containing this set of unique smallest tree containing this set of vertices. Then the remaining feasible subsets form a delta method, and this delta method is different from the blow-up delta method. And so here it is that this new delta method is a superset of the block delta method for the path graph on K nodes for K different. We also showed in our paper that this construction does not extend to the arbitrary. To provide an example, okay. So, one can find the more details about this result in this treatment. Thank you.
Yeah, thank you so much, Projesh, for the interesting talk. Audience, if you have any question, you can ask now.
Hello.
Yes.
Hello. I have one doubt.
Yes. Tell me.
So can you go to number slide 4, 4 or 5? Yes. Next year, this is a 1, 2, 3, 4 cycle, and next you showing the determinant next step.
Yes. Yes.
Yes, this is the determinant.
Yes.
So we know the distance eigenvalue of the cycle for n even order is eigenvalue of 0. So here determinant must be 0 here. So how can I get 0? Putting R and S is some value, maybe it's 0.
Okay. Yes. For this is 12, and okay. So if you can put R and S equal to 2, because the complete graph, yes, for cycle, I told you that you just look at this and two copies of the vertex 1, that is R is 2, and 2 copies of the vertex 2, that is S is 2. Okay. So this quantity is 4 and 12. Okay. And plus 4 is 16, and here it is 8 minus 8 minus 8. So it's 0.
Oh yeah, thank you. Yes, got it. Thank you.
Okay, are there other questions? Okay, if not, thank you, Projesh. Thank you so much.